In this collection of videos, we're going to do one example involving a Riemann sum, and then we're going to try to move on and define something called a definite integral that's going to help us compute the values of these Riemann sums a little bit faster. So just to review this idea of Riemann sums, we're working with some type of function f of x on this closed interval from a to b, and we're breaking up the interval from a to b into n rectangles, where all of our rectangles have equal width. For that reason, if we're looking at the width of a rectangle, it's going to be given by the length of the interval divided by the number of rectangles we have, and it's appearing in this sum that we see later down on the slides, right here. Now, in order to figure out the height of the rectangles that we're going to be computing the areas of, we'll be using the height of the function. And in order to do that, we've got to make some sort of choice about how we're going to label the a sub i's along the x-axis, where the a sub i's are coming from the endpoints of these little sub-intervals of our entire interval that's going from a up to b. It therefore becomes the case that if we want to consider the area of one of these individual orange rectangles pictured over here on the right, we're going to find it by computing its width times its height, where its width is given by that value, b minus a over n, that we discussed previously, and its height is given by evaluating the function in question, f, on one of the a sub k's, where we're using the a sub k equal to the leftmost endpoint of that interval. Now, there are other options that you could choose for what you're going to use for the height of your rectangles, including the rightmost endpoint of the interval, perhaps the midpoint of the interval, or there are some other choices that you could make. But in order to make things consistent and nice within this summation, we've labeled our points a sub I on the interval in this particular way, and we've chosen the left endpoint here. So what this summation is indicating is that we can find the total area in orange, pictured on the right, by summing, the sigma is a Greek S for sum, the individual areas of the rectangles, and the individual area of the rectangle from a sub k to a sub k plus 1 is given by this expression right here, the width of the rectangle multiplied by the height. Now, it should come as no surprise to us that the more rectangles we use, the better our area approximation becomes. So in theory, if we take that sum, which was representing the total area from the previous page, and we take the limit as n goes off towards infinity, the number of rectangles we're using is becoming infinite, then our approximation should get closer and closer and closer to the actual value of the area underneath that curve. And so this is something that we're going to want to evaluate. And when we take this limit as n approaches infinity, this is where the difference between did I use the left endpoint or the right endpoint or maybe the midpoint, all of those things become irrelevant as we cram more and more rectangles underneath that curve. Those values for the different heights of the rectangles we could have considered become negligible in this limit, and so we really are free to choose if we want a left endpoint approximation, a right endpoint approximation, or something else. We'll end up with the same limit value no matter what. So for the remainder of this video, I'd like to take a look at doing a computation involving this limit of a sum of individual areas the long way. So for our example, I'd like our function to be the function 1 minus x squared, and I'd like us to work on the interval from 0 to 1. We're going to come up with an approximation for the area between the function f of x and the positive x-axis on that interval from 0 to 1 by coming up with a formula for a Riemann sum using n rectangles, where n is going to be a variable for us. After we've come up with a formula for that Riemann sum, we're going to use some summation formulas that will probably not be known to you, but are the types of things you could look up in order to determine the value of that Riemann sum as a function of n. At that point, we'll just be looking at a function of n, and we'll be asked to determine the limit of that function. That's a thing we're already familiar with doing in a calculus class, and that limit from part 2 as n goes off to infinity is going to be the actual value of the area between this function, 1 minus x squared, and the positive x-axis on this particular interval. So, for this specific example, the a that I mentioned on our first slide is 0, the b that I mentioned on our first slide is 1, and because we're using b minus a over n as a formula for the width of our rectangles, we end up with a 1 minus a over n, or a 1 over n, as the width of each of our rectangles. The a sub k's that we had marked out along the positive x-axis that were defining these little sub-intervals, which were the endpoints of the base of the rectangle, our a sub k values then become k over n. We're just adding that increment of 1 over n, starting at 0 and doing that repeatedly to define the kth endpoint of the interval. And if we plug those things into the Riemann sum without the limit that we saw on our very first slide, we have f of a sub k as k goes from 1 to n, this piece defining the height of our rectangles, and 1 over n denoting the width of our rectangles. And all that happens moving from left to right here is that we substitute in what a sub k is, according to this equation, into our f of x equation, according to this equation. So combining those things together, this generic Riemann sum over on the left becomes the more specific Riemann sum over here on the right. Now the next thing that we want to do is break this sum down into the smallest pieces possible to focus our attention on things individually. So for example, when we have a sum, as we do here, and we have the same expression appearing in each term of the sum, 1 over n, that thing could be factored out by the distributive property and removed from the sum entirely. So the first change that we see from this summation to this summation is that the 1 over n has been factored out. Then I'm just left with a 1 right here, and the k over n squared, I've distributed that square to both the top and the bottom of my fraction right here. Now the next thing that you'll notice is different from this piece and this piece is that I actually have two different summation signs. While the top sum is stressing that I have this one thing minus another pattern in each individual addend, what this expression is saying is that I could just add together all of the ones that I'm going to occur, and I could add together all the k squared over n squared pieces that are going to occur, and I could regroup. In other words, I could rearrange the order in which I'm adding things and add them separately, because addition is a commutative operation. And so that's what I've done here, is I've done a couple of things. First, I've factored the 1 over n that I'm multiplying each addend by out of the equation. So I have 1 over n at the front and then parentheses around everything that's left over. Second, I've distributed that square to the top and bottom of this fraction so that I have a k squared over n squared. And last but not least, I've rearranged the summation using the commutative property to add all the 1's first, add all the k squared over n squared second, and then lastly do that subtraction. So that's how I've gotten from here to here. In this very last equality, not much has changed other than the 1 over n squared has again been factored out to the front of this summation because each term in this summation is being multiplied by 1 over n squared. So I'm just factoring out the 1 over n squared in the same way that I factored the 1 out of n from this entire expression. If you're looking for a real quick short rule for when can I factor something out and when can I not, the real answer is something can be factored out of the equation if the piece that you're multiplying each of the addends by does not involve the variable that you've introduced in your sum. So this 1 over n didn't involve a k at all, so I could think of it as a constant and factor it out of the sum. This 1 over n squared didn't involve a k at all, so I could factor it out of the summation right here. but because the k's truly are changing as the k changes from 1, 2, 3, 4, all the way up through n, that's not something that can be factored outside of the sum. Now on the previous slide we had two different summations, and we had narrowed down those summations to be as little as possible in order to simplify this part of the problem as much as we could. This first summation, just summing the number 1 a total of n times, is really easy to think about. Summing the number 1 n times is just going to yield a value of n. However, that other term, this sum as k goes from 1 to n of k squared, that's not something that I just happen to know an intuitive answer for what that sum is equal to off the top of my head. However, this type of a sum has been studied quite a bit historically, and there was a theorem that's often credited to Archimedes. It's difficult to say whether that's truly his theorem or not, but a theorem that is often accredited to Archimedes tells us that we can determine the sum from 1 to n of k squared to be this cubic equation over here on the right. Now that's not a thing I would expect most people to know off the top of their head, but in computing Riemann sums, it is an example of a sum that comes up a lot, so it's a good one to just have a reference for. If we make those two substitutions for the summations that we're considering here, we can get rid of all that ugly sigma notation and replace the sum of n ones by a value of n, and replace this sum as k goes from 1 to n of k squareds by this formula due to Archimedes right here. But we have to remember to multiply by the 1 over n squared, so this n squared that we're seeing in the denominator that differs from the formula up here is coming from the 1 over n squared coefficient we have right here. And this is the function that we have that is equivalent to that Riemann sum. Simplifying a bit, in particular distributing that 1 over n to each term of our parenthetical expression, we end up with this formula 1 minus this particular cubic in the numerator that's factored, and this 6n cubed in the denominator. That expression is simple enough that I'm willing to take a limit of it, which is the final thing we need to do in order to determine the real value of this Riemann sum, is we need to take that limit as n goes to infinity to envision putting as many rectangles as possible underneath this curve. This limit, focusing on n behavior of the numerator and denominator in that second term, is equivalent to the limit 1 minus, the limit as n goes to infinity of just those leading coefficients, 2n cubed over 6n cubed, which simplifies to a 1 minus a third, or 2/3. Now, that was a lot, and in general, that's the way these Riemann sum problems go. They are a lot. You've got to write down a formula for that Riemann sum, which by itself is fairly complicated. You've got to substitute everything in for your specific values and do a lot of algebra with this clunky sigma notation just in order to come up with a really nice number at the end. They're doable, but they're very computationally intensive, and you've got to be very driven in order to give that result. What's going to be coming in the next video is a huge upgrade from those Riemann sums. It might not seem like it at first from these videos, but we're going to develop some really cool tools to do everything that we wanted to do on the previous slide, which was determine that area beneath a curve and the positive x-axis on this closed bounded interval in a much better way. So this is a really nice graphic to think about the transformation that we're going to be having coming up. It's due to Howie Hua, a great mathematician. You should definitely look him up. And this shows the evolution of a porygon to a porygon 2, which if you're following along from my class, is a great answer to a quiz question. Stay tuned.